is an exponential function? An exponential function can be written in the form of f of x or y equals a to the power of x, where a is a constant value and the base of the function, while x is the variable by which the graph increases or decreases by. You can tell if a function is exponential or not by determining the ratio of consecutive y values. If the ratios are constant, that means that the function is exponential. This can be seen through the example y equals 2 to the power of x, where the y values are 1, 2, and 4 as follows. In order to find their ratio, we use the formula y2 over y1, which ends up giving us a ratio of 2. And since this is a consistent value, this means that y equals 2 over x is therefore an exponential function. Now this ties in with exponential growth, which is what occurs when the independent variable increases by a common amount, which in turn causes the dependent variable to increase by a common factor as well. It is a fixed period over which the function will increase in increments. This can be seen through the function y equals 3 to the power of x, where x is the exponent or variable that increases in increments of 1 each time, while y is the base which triples each time that the exponent is increased. This can also be seen through the graph where y triples each time that x increases by 1. Therefore, the value of y is dependent on the value of x. Also a note, any exponent raised to the power of 0 equals 1. So when 3 is written as 3 to the power of x, we can assume that the first exponent would be 0, which means 0 would have a value of 1. Now, in order to represent exponential growth, we use the model Pn equals P0, 1 plus r to the power of n, in which Pn equals the total amount or final number, P0 is the initial amount, 1 plus r equals the rate of growth. R specifically equals the rate of growth, but we use 1 plus r in this model as any function with a base larger than 1 represents an exponential function that is increasing. And finally, n is the number of growth periods. Now let's try an example problem to make sure that we fully understand this concept. In 2002, it was recorded that 200 pangolins were born annually in Africa. The population of pangolins has grown at a rate of approximately 2.4% per year since then. Let's answer part A. So in order to create an algebraic model specific to this problem, we are given the values, our initial value, which is 200, and we are also given our rate of growth, which is 2.4%. In order to convert this to a decimal, we can just divide by 100, which gives us 0.024. Now we can sub this into our original growth formula to get the following answer. Now let's answer part B of the question, which is, what will the population be in 20 years? Now we are given an n value, or the number of growth periods in this case, which is 20. So using that, we can sub it into the formula we found beforehand in order to get an answer of p equals 321.
An exponential decay is a decreasing pattern where each term is multiplied by a fraction between 0 and 1, allowing for a repeating pattern of finite differences. In the table below, the finite differences can be calculated using the formula y2 over y1 to get a constant ratio of 1 over 3. An exponential decay produces a graph that decreases at a declining rate. For example, if we were to plot the points identified above, our graph would look as such. An exponential decay can be modeled by the following equation. Pn equals Po, 1 minus r to the power of n. This is the same equation as y equals ab to the power of x, since b can be equivalently written as 1 minus r. Recall what each variable represents in the equation. For a better understanding of this concept, let us look at an example for an exponential decay problem involving half-life. Half-life is defined as the length of time a radioactive substance takes to decay or decrease to 1/2 of its original amount. The question is, one isotope of lead-210 has a half-life of about 20 years. A sample contains 210 grams. A. Write an equation to model the situation. From the question, we have been told that the initial value is 210. n equals t over 20, where t represents the number of years gone by, while 20 years is one decay period. From the problem, we can determine that the rate of decay is 1/2. So we can replace b, or 1 minus r, with 1 over 2. If we were given a percentage as the decay rate, we would only replace r in the equation with the appropriate decimal. Therefore, the equation can be written as Pn equals 210 1/2 to the power of t over 20. B. After 60 years, approximately how much of the initial amount is left? To determine how much of the substance will be left in 60 years, we must substitute 60 in the place of t and solve. Therefore, 26.25 grams of the substance remains. C. How many years would it take to get the material to be 1/5 of its original amount? To determine how many years it would take, we must first calculate 1/5 of 210 grams, which is 42 grams. Then we must replace the variables within the equation with the known values to isolate for the n value. Once we have isolated for the n value, we must use the log function on our calculator to solve for t over 20. We can write the log of both sides as log 42 over 210 equals log 1/2 to the power of t over 20, but the property of the log function is that it's going to bring the exponent down. The equation will then become t over 20 log 1/2 equals log 42 over 210. To isolate for t over 20, we must divide both sides by log 1/2. By doing so, we get t over 20 equals log 42 over 210 over log 1/2. Note: when using the log function to bring the exponent down, it applies to the entire n value, and that is why we cannot directly solve for t. Therefore, when evaluated, t over 20 equals 2.32192. To solve for t, or the number of years, we must multiply both sides by the denominator, or 20, to get a final rounded answer of 46.4 years. So far, we have considered situations where n is greater than or equal to 0. However, you will sometimes encounter exponential expressions with negative exponents. You can use the following relationship to evaluate expressions involving negative exponents. The power laws still apply for powers involving negative exponents. To solve the example below, we would first take the reciprocal of the power to get a positive exponent. We would then apply the power of a power rule to get a final answer of 1 over x to the power of 6, y to the power of 8. Rational expressions raised to a negative exponent can be simplified by flipping the numerator and the denominator to get a power with a positive exponent. 4 over 6 to the power of negative 1 can be written as 6 over 4 to the power of 1. If a number in the denominator is raised to a negative exponent, when expanded and simplified, this power becomes the numerator. An example of this is given below, where we must apply the negative exponent rule. Therefore, 1 over x to the power of negative 9 equals x to the power of 9.
The exponential function has an equation fx equals ab to the power of x, which we will be observing the characteristics and properties of this function. In the equation fx equals ab to the power of x, if b is greater than 1, then the graph would be increasing. In other words, it is an exponential growth, so the greater the b value, the faster the growth. The function looks something like this. It increases from the left to the right. For example, in the blue is fx equals 2 to the power of x, and in the red is fx equals 4 to the power of x. The red one has a steeper shape than the blue as the b value is greater. But if b is greater than 0 but less than 1, the graph would be decreasing. In other words, it is an exponential decay. The smaller the value of b is, the faster the decay is. The function looks something like this. It decreases from the left to the right. For example, in the blue is fx equals 0.5 to the power of x, and in the red is fx equals 0.25 to the power of x. The red one would have a steeper shape than the blue as the b value is smaller. For an exponential growth or decay, they would both have a domain xer, which means x is a set of real numbers. They would also both have a range yer, y is greater than 0. The horizontal asymptote is y equals 0, but it would change if the graph was shifted up or down. The y-intercept, whether it is an exponential growth or decay, will have a y-intercept of 1. To match these graphs with the following equations, we can use the exponential properties we just learned to help us figure that out. Graph A is an exponential decay, which means the b value is greater than 0 and less than 1. That means that the equation that matches the graph is y equals 3 times 1/3 to the power of x. Graph B has been reflected in the x-axis, which means using the function y equals ab to the power of x, or fx equals ab to the power of x, there will be a negative sign in front of the a value to indicate that it's been reflected. By observing this graph, we can tell that the b value is greater than 1, which means that the graph has an exponential growth. That means that the equation that matches the graph is y equals negative 3 to the power of x. Now we'll do another example. Graph each function and identify the domain, range, x and y intercepts if they exist, and the asymptote. To graph fx equals 1 over 4 to the power of x, we substitute x values such as 0, 1, 2, 3, and you get the y values 1, 1 over 4, 1 over 16, and 1 over 64. Plot these points on the graph and connect, and as you can see, the b value is greater than 0 but smaller than 1, which is why there's an exponential decay. To graph y equals 3 times 2.5 to the power of x, again we substitute x values such as negative 1, 0, 1, and 2, which is what gives us the y values 1.2, 3, 7.5, and 18.75. As you can see, the b value is greater than 1, which is why there's an exponential growth. To graph y equals negative 1 times 1 over 5 to the power of x, again we substitute x values. Let's substitute x values 0, 1, 2, and 3, which gives us the y values negative 1, negative 1 over 5, negative 1 over 25, and negative 1 over 125. And as you can see when you plot these points that the b value is greater than 0 but less than 1, which is why there is an exponential decay. As mentioned, the a value has a negative sign, which is why the graph is reflected in the x-axis. Overall, they all have a domain, xer, and an asymptote equal to 0. Graph A has a y-intercept of 1, graph B has a y-intercept of 3, and graph C has a y-intercept of negative 1. The range for graph A and B is yer, y is greater than 0, and graph C has a range of yer, y is less than 0.
First of all, recall that in the equation, A is the vertical stretch or compression, K is the horizontal stretch or compression, D is the horizontal translation, as in right or left, C is the vertical translation, as in up or down, and B is the constant, which is always positive. So the order of the transformations is important. So in graphing, you start off with a stretch and reflection and then end off with the translations. You graph an exponential function in the form of y equals a times b to the power of k times x minus d plus c. The mapping notation is 1 over k times x plus d, and then a times y plus c. So when you're sketching exponential functions, you must always include a horizontal asymptote, and then there should always be a y-intercept, and include an x-intercept if there is one. You should plot at least 2 negative x values and 2 positive x values. You should always state the domain and range. For example, let's look at the equation fx equals negative 2 times 2 to the power of x minus 3 plus 4. We'll first start off by graphing the base graph, which is fx equals 2 to the power of x. So 2 to the power of 0 equals 1, so that will be your first point. And then 2 to the power of 1 equals 2. That will be our second point. We keep doing it until we have our complete graph. Now we will graph fx equals 2 to the power of x minus 3. For this, we will move the x values of the base graph right 3 units. So let's start. Now you will graph fx equals negative 2 times 2 to the power of x minus 3. For this transformation, the y values we got from the previous graph will be multiplied by negative 2. Since this a value is negative, there will be reflection on the x-axis.
Now to get the final graph of fx equals -2 times 2 to the power of x minus 3 plus 4, we need to shift the graph up by 4. And with this, we have the final graph. As you can see, the asymptote of this graph is 4, the domain is x is any real number, and the range is y is less than 4.